Thank you. First sound check. Can you hear me also in the back? So I'm holding this right. Very good. Thumbs up. Yeah, my pleasure to be here. My talk is called Learning the Next Generation of Maps. I'm Eric. I'm a scientist at Niantic Spatial. I'm active on social media, at least the nicer ones. I hope that helps with the Nobel Prize. Now I just have to get the research right, I guess. Niantic Spatial is a fairly recent startup. It emerged from Niantic, the creator of Pokemon Go and other location-based games. But the goal of this new startup, Niantic Spatial, is, well, to map the world, but with a new kind of map, a geospatial model, which allows for semantic understanding and nice reconstructions and also advanced navigation and visual relocalization. So Niantic Spatial traces back to Niantic and to Google Maps and Google Earth and back to a startup called Keyhole. So the founders of Niantic Spatial have a lot of experience and a lot of background in mapping. And it turns out so has humanity. So according to Wikipedia, this is one of the oldest surviving maps that we know of. It's engraving on a mammoth tusk, I think, and it's 25,000 years old, and it's from Czech Republic. I think they found this. It's a 3D object, but actually it's a 2D map engraved onto a 3D object. So actually it's not so different from the maps that many of us use still today. So we are familiar with this on our phones. But a few decades ago, maybe even centuries ago, people started to think about what other kinds of maps could you build. And there was this, from computer vision and photogrammetry, this idea to build 3D reconstructions from images, and these can also serve as maps. And that's quite nice, actually, because it allows you to estimate your position in 3D space, so with orientation and with translation, and that's really nice. And it works really well, too. But of course, as researchers, we are never satisfied. So we might wonder, well, but what's the next stage? What comes next in terms of maps? What could be the next generation of maps? I don't know. I have no clue. I don't know how it would look like, how it would be structured, and what information should be in there. Maybe you have an idea. I don't have one. But maybe I don't need to know what it looks like. Maybe it's enough if I come up with a functional definition of a map. Maybe it's enough to say what I want to do with the map, right? And one important thing which you might want to do with a map is to know where you are. You want to relocalize, right? And then another question you might want to answer is, what do you have available to build the thing? And in the case of this talk, let's say we have images. And whatever a map is, whatever it looks like, we want to create it from images and we want to use it to relocalize. And of course, if you look at these boxes and how it looks like, it's actually a great match for machine learning, because you just define what you want to solve and what the inputs are, and then machine learning allows you to create whatever is in the middle. You don't really care what it is. You just optimize it, right? And that is what we are trying to do. The task that we see here in the research context is called visual relocalization. So let's look at that task. We heard it a few times in these talks, but I present it again. It consists of two stages. You have the mapping stage, where you go to a new location and you take many images, and from those images you create your map, a scene representation, which could be a point cloud, which you create from these images. And then there is the second stage, the relocalization stage, where you or another user goes to that same location and takes a picture. And now you want to estimate the camera position and orientation with respect to the map that you have built earlier. And as I said, we can do this with classical methods very well and for a long time. Quickly show you how it works with classical feature matching. So like running CallMap, for example, you have your images and you start with two images with a pair. You find correspondences, which allows you to estimate the relative pose between those two images. And then with the relative pose, you can triangulate the points. And then you start adding other images. So you look for a third image where you can observe the same key points. And with those correspondences, you can register the new image to the partial point cloud that you have already The new image allows you to triangulate more points. And if you repeat this with all your cameras, you get all the camera poses and you get a nice point cloud of the scene. Okay, that's the mapping stage. The relocalization stage looks like this with feature matching. So you get your new query image. First, you have to figure out which of the places that you have reconstructed do you actually want to relocalize against. So you can do this with a GPS prior or with image retrieval to find the map that is actually relevant for your query image. And then you go on finding key points again in your query and you match it against the key points that you had in your mapping image. And because you have triangulated all these points already, these are actually 2D, 3D correspondences. So you can just feed them to Ransack and PNP, and you get the pose of your query image with high accuracy as well. So this is the classical approach built on 3D point clouds with high-dimensional feature descriptors. Okay, so let's look at other possibilities of how to do this. Part 1, mapping with scene coordinate regression. So in this approach, we actually stay quite close to this classical pipeline. We just merge 2 steps. We merge the feature extraction and the feature matching step into one step, which is correspondence regression. So let's look at an example. We have a query image here, that's an indoor scene, and the corresponding room looks like this. It's visualized as a point cloud again. And we want to solve this with a neural network. So what's the task of the neural network? Network should predict, regress correspondences. So you can imagine each point on the surface of this room lives in its, has a unique 3D coordinate in the reference space of that room. So we can visualize these 3D coordinates by mapping those to the RGB cube. And the task of the network is to predict these scene coordinates. The cool kids these days, they call these predictions point maps. But in the context of these works, here they are called scene coordinates. But it's the same thing, actually. So this is what the network should predict. And we train, or with this output, we have 2D, 3D correspondences, which we can again feed to Ransack and PNP and solve our relocalization problem. That's the relocalization stage. So what's the mapping stage? The mapping stage now is actually training this network. And different from feed-forward methods like Duster, these networks are trained per scene. So you build a network for a specific scene. You assume you have training data, you have images and poses. You feed them into the network at training time to you optimize it, right? You train it per scene. So what in this context is now actually the map? The map is the network itself. Through our training, it encodes somehow the geometry of the scene into the weights of the network. So the network itself becomes the map. So what does training exactly look like? We want to train it just with RGB images and poses. We don't know the geometry of the scene. We don't have depth estimates. We really just have the ground truth poses of our mapping images. So through our training, we can take a mapping image, which in this case is actually a training image, and the network predicts something. And with the ground truth camera pose, we can define a reprojection loss. So this is the formula. The network predicts a 3D coordinate for a pixel. We have the ground truth mapping pose, which we can use to transform the 3D coordinate in scene space to camera space. Then with the known intrinsics, we can project it into the image, and when we can penalize any divergence to the 2D pixel position that the coordinate was predicted for. So it should be self-consistent with respect to the pose that we have. There's one problem with this formula. It's the depth of the scene coordinate is not constrained. So anywhere along the pixel array, any scene coordinate prediction along the pixel array would satisfy this formula. But it turns out that through our training, when the network sees many different views of the scene, it converges to a multi-view consistent solution. So And the multi-view consistent solution is the one where the scene coordinate has the correct depth. So throughout training, actually the network automatically recovers the geometry of the scene. And when we did this the first time in 2018, people were actually surprised that it works. That just from RGB images and poses, with just optimizing single view constraints, still the network somehow figures out the 3D geometry of the scene. And then at relocalization time, you can just feed in images, you predict scene coordinates, you can relocalize with high precision. And it's actually quite fast at this stage, because the network predicts directly the correspondences that you need. Network is quite small. The correspondences are rather friendly, so you get away with a nice, simple ransack. So in 20 milliseconds, you have your pose estimate. And that's quite nice and fast. What wasn't so nice and fast was the mapping time. Because mapping, in this case, means you train a network, right? So the training time of the network is your mapping time. And that took a few hours for each new scene. And that's, of course, bad. We tried to address this problem in a paper in 2013, which is called ACE, Accelerated Coordinate Encoding. And the main idea is actually quite simple. You change the pipeline and the recipe to go away from an image-based optimization to a patch-based optimization. And that changes a lot. So it doesn't change the pipeline too much, but it changes a lot the outcome. So you have your mapping images, potentially hundreds or thousands of them, and then you randomly sample patches from these mapping images. And these random patches make up your training batch. You feed this into your network, which consists of a frozen encoder. So for each patch, you get a high-dimensional feature. And then this thing that you actually want to train during mapping time is just a small MLP, which maps the high-dimensional feature to the 3D coordinate. And because you have randomly sampled your training patches, actually during the loss prediction or the loss calculation, you also have random samples of scene coordinates throughout the entire scene. And each scene coordinate prediction is supervised with its corresponding pose. So you basically supervise with all your camera poses at once, at the same time. And that makes the optimization much more stable than it was before, and it converges much faster. So here's a one-to-one comparison. Left, there is the old system, which used this image-based optimization and took 15 hours to train. And then on the right, you see ACE, which converges after 5 minutes, so 2 orders of magnitude faster. And then at test time, nothing changes. So you still relocalize in 20 milliseconds with the same accuracy. So it really just makes everything faster during mapping time, and otherwise you have the same nice system as before. So that was cool, and it was also important for the company somehow, because if you want to deploy this at scale, then of course it matters how much training time you have for each individual network. And at Niantic, we are building this visual positioning system, and ACE is part of that. So there are a few million locations worldwide where you can go and where we have built maps. And in the scope of this, we have trained 70 million ACE networks by now. And of course, you can imagine if each network would need to train for 15 hours, you wouldn't be able to do that. Right. So the system is actually quite nice. It trains in 5 minutes. It takes 20 milliseconds to relocalize. And as I said, you can train it with RGB images and poses, and people were surprised that it works. When we were thinking, maybe we can push it even further. Maybe you can even take away the poses and do it without the poses. So part 2, the Münchhausen trick of getting poses. If you don't know, Münchhausen is a Baron Münchhausen is a fictional character from German literature who pulled off or is famous for pulling off many impossible stunts. And one of the impossible stunts that he did, supposedly, it's fictional, is that he pulled himself out of a swamp. So he grabbed himself on the head and then just pulled himself up and out of the swamp. So we will try to do something similar with ACE. And that would actually be quite cool, because if we could handle just an image collection without poses, then we would turn A's from a visual relocalizer to a structure from motion tool. That would be kind of nice, right? So how do we do that? Again, in hindsight, it's quite simple. Maybe the most surprising thing is that it works. The key insight is, well, you know, you want poses. You have a method that estimates poses, right? ACE is a pose estimation method. So if I have a scene like this, and I have the images with the orange poses, I can train an ACE network. And if I get a new image without a pose, then I can apply the network, predict scene coordinates. These are 2D, 3D correspondences. I can feed them to RANSAC and PNP, and I get this new pose of a new image where I didn't know the pose before, right? You can imagine, well, if I would retrain now with this additional image, maybe the network gets better. And that also works backwards. So maybe I don't need those poses here in orange because I can estimate them with a model that was only trained on the blue camera poses. So those poses go away. I don't need them. And maybe I can go on like this. Maybe those poses I don't need because I can estimate them with a model that was trained on these blue camera poses. And maybe those poses go away because I can estimate them with a model that was trained on these poses. And maybe these poses go away if I would be able to estimate them with a model which was only trained on a single image and a single camera pose. So what's the first camera pose? That's identity, that's easy. But can I train an ACE network with just a single image and an identity pose? Not as I have explained so far, because I said if I optimize the reprojection error, I need multiple views to constrain the depth of scene coordinates, right? So here, for the very first image, we have to do something different, but it's quite easy, actually. We just take this first image and we apply an off-the-shelf depth estimation network to initialize the geometry, basically. So we unproject it, we get ground truth scene coordinates for this first image, and then we can actually learn the first model. Right. So there's another problem we have to solve, and this is, if I want to retrain on the estimates of ACE itself, I better make sure that these estimates are good. And the model will fail on some images, right? Especially in the beginning. So if I have like a difficult image, a bad image, like this one is from the other side of this truck, then ACE might predict poorly, might predict garbage. And I don't know upfront, right? So I take it, I feed it to RANSAC and PNP, and I get an outlier pose, an arbitrary pose. It's just the optimization phase. The nice thing about ACE, though, is that it's a correspondence-based method, so you can always count inliers. You can check how many scene coordinates are how many scene coordinates are consistent with the estimate of RANSAC and PNP, and then you can just say, no, it's not consistent, it's low inlier count, I reject it. And it turns out that this criterion is relatively stable in deciding success versus failure of relocalization. And again, with ACE, this is quite fast. So in 20 milliseconds, you can do this decision. So in every stage of this incremental training, you can just try all the different images and see whatever you can already successfully relocalize. And those images you add to your training set and you retrain. Right. So this approach is called ACE0 because because we trained from scratch in a self-supervised fashion, and ACE because it's building on the ACE relocalizer. This was an ECCV 24 paper. The method name is not in the title, a choice that I cannot recommend in hindsight. But yeah, it's called scene coordinate reconstruction. Right, and let's now look at how it actually reconstructs a scene, this scene here. Here we see a dozen images also, something which you could easily do with a feed-forward method as well. You could run VGGG or even Duster Master on this. The advantage of ACE and ACE0 lies in handling many images. So we can actually run this on thousands of images. Here we have 7,500 images. The underlying thing here is a video, so I just took every frame of this video that we had, 7,500. I shuffled them, so there's no sequence. And that works with ACE because you randomly sample across the whole mapping sequence. The more, the merrier, right? And then pose estimation itself is also fast, so that's really an advantage, I would say. You can compress all these thousands of images into a relatively nice, compact scene representation. Okay, let's start. We have 7,500 images, but we still start with a single one. We randomly choose one as our seed, and then we have the depth prediction network, which for this very first image predicts a depth map, and we fit the first relocalizer to that. So we optimize the distance to the ground truth depth, and that gives us the initial ACE network. And now we just run all 7,500 images through the relocalizer and decide whether it's success and failure. And you see green frustums and yellow frustums, which are kept. Those survive the test. And the yellow ones, they are barely above the inlier threshold. So they are quite uncertain, and maybe you can guess that they are also quite noisy. Probably the camera didn't move like that. They are quite dispersed. So in the next training iteration, what we also do is refine these poses, and that's actually quite simple because we just backpropagate the loss of the reprojection error loss, not only to the network, but also to the poses. And because they are already roughly in the right space, that works out. So in the next training iteration, you can see the poses snapping onto what probably is the correct trajectory. So this is, well, there's some analogy here to bundle adjustment, I guess, but yeah, it's optimizing jointly the geometry and the poses without doing much, just backpropagating the loss, which I think is nice. Okay, now you have a new relocalizer, and you can relocalize more images, and you can do this in a loop. You see that the trajectory grows around the truck until we have posed all the images. In the back, there, if the two trajectories meet, there will be something like loop closure happening here now, but it's all doing it by itself. It's not modeled in any way. It's just trying to find a multi-view consistent scene representation, and everything somehow emerges magically. And then at the end, we have posed all the 7,500 images. In this case, it took 1 hour on a consumer-grade GPU, so you don't need a big GPU to do this. Right. The output are the camera poses. That's the main output. You also get a coarse point cloud, but as you see, it's not looking so nice. But it's good enough to initialize Gaussian splats. So you can do nice things, and you can check whether the poses are all right, look okay. Right. Here's a different example. On the left, you see the input video. On the right, you see the reconstruction. The input does this strange motion. Because I had the visualization code already, and I wanted to write out A0 with the camera, and yeah, I halfway succeeded to do this. So if we go back to thinking about or appreciating that this works, I still find it kind of amazing, because people were surprised that you can do it with RGB images and poses, and it converges, right, to something multi-view consistent. And now we even took the poses away, and we only optimize single view constraints. So what is holding it together? I can only guess, but my guess is that the network is a fully convolutional network, so it has a smoothness prior. When the input changes only slightly, because the viewpoint changes only slightly, the network is biased to predict an output which also only changes slightly. So the smoothness prior, I think, of the network is holding this whole thing together, but not always. There are cases where it doesn't work. So here we have an indoor room. I don't actually know what the problem is here. Maybe there are walls without texture which are breaking it, but if we try to reconstruct it, you see there is this lump in the middle that might be the room, but there's a lot of stuff going on far away, and you don't see this here, but there are also cameras floating in space. That's why the visualization zooms out, because it tries to capture everything. And at the end, you get a broken reconstruction. And you see this also in the depth histogram that I plot. There are many scene coordinates far away from their cameras, something which you definitely would not expect for an indoor room, right? So, what do? Part 3, we talk about priors. There are many different priors which we could try to add to this to make it more stable. The simplest thing you can do is utilize additional information if you have it. And information that is relevant here is depth. If you have depth, everything becomes very easy and very nice. Because then you can just, if you have a predicted depth of a scene coordinate and you know what the depth should actually be, during the optimization you could just pull it there. You could just say, you add a regularization term and say, this is the actual depth that it should have. And this is super simple and it actually works very nicely. So this is basically just an RGBD version of A0 and it's working really well without doing crazy stuff. It's just nice. So the same reconstruction now is actually successful. Okay, but of course it depends on you having this additional information and sometimes you don't have it. What else can you do? And this is actually now a difference to feed-forward methods. Feed-forward methods can also utilize additional information. I think it's called power, one of those, right? With power. With these optimization-based approaches, you can do different things. So you can think about, okay, maybe if I know some statistics of my scene that I know should hold, I can optimize that throughout the reconstruction. So for example, if I don't have depth, I can still say, well, for an indoor room, I expect a certain distribution of depth, right? Maybe some small depth values, the majority should be somewhere in the middle, some larger values, but no extreme values, right? So a certain distribution that I would expect. And then I can compare this to the distribution that I have. And I can penalize if this diverges significantly. For example, one way, which I find nice, is the Wasserstein distance between these two distributions. The empirical distributions that you have during reconstruction and the distribution that you define as your prior. And this you can just add to the loss. And now we see the same scene again with this Wasserstein regularization. Yeah, and it holds everything together. So you see in the depth histogram, basically the prior is trying to push the distribution to be more like what we expect. But still there's a reprojection loss to counteract that if necessary. And in this case, again, the reconstruction looks pretty similar to the one that we had when we had depth values, right? So that's nice. Okay, but I think there's one more level. The ultimate level of enlightenment is using generative models. Because if the scene level statistics, they are somewhat handcrafted. You think about what statistics do I want to optimize, what should be the parameters and so on. With generative models, you have a learning-based approach to do this. And this is quite nice because it allows you to do the following. Let's say you have a data set of successful reconstructions. Let's say you have reconstructed so many indoor rooms already, you know what they look like, right? You have a data set of many of these floor plans and so on. And you want to somehow distill this knowledge into a model that knows what an indoor room usually looks like. In our case, this will be a 3D point cloud diffusion model. So it takes 3D noise and diffuses it to a point cloud which could be an indoor room. Right. How do we use it? So first it's pre-trained. It's distilling knowledge that we already have and then we keep it frozen. And then there were clever people showing that this formula holds. Basically, if a diffusion model predicts the noise at the current time step, this is proportional to the gradient of the log probability of the data that you have. And that's exactly what we need. So this is a perfect match to an ACE-like system because in each step, ACE predicts a point cloud and the prior could tell it, well, to make the point cloud more plausible, nudge the points to a more plausible configuration. So we just feed those gradients of the diffusion model to the optimization, and this also regularizes the reconstruction, and we get a nice camera trajectory again. Without us thinking about priors, just learning from successful reconstructions. And this I find conceptually very, very nice. All right, this was a ICCV 25 paper where we investigated all these priors. The priors themselves are not new, they were used in different contexts already, and here we show that you can also use them for scene coordinate regression. Right, so looping back to the beginning of my talk, what's the next generation of maps? maybe it's a network. But I'm not convinced, because that's weird. And an MLP of all things, it's not even a transformer, right? It's just an MLP. No, there has to be something else. So part 4, rebuilding the world in latent space. One limitation of ACE is that it generalizes fairly well to new query images until it doesn't. At some point it fails to generalize and it breaks down, and there's not much you can do about it. Because in this case, for example, we have in the room, we have our mapping images, we fit a network which represents our scene, and then you get a difficult query image. And this query image here is difficult because it is a large viewpoint change. It's basically a viewpoint of the scene that you have not seen before. And ACE fails. So the estimate is far off. It's just the viewpoint change is too big. And the problem is, what do you do about it? It's not easy to, there's no way to somehow teach the model to cope with this, because the model by definition in scene coordinate regression, it was overfitted to your mapping images. If you don't have this viewpoint, how do you teach the network to solve it? Because it knows only this world. The world that the network knows is restricted to the mapping images that you showed it. And this is exemplified here in this toy example. What we will see when I start the video is a 360 circle around a tabletop setting. The mapping images are the small part below of the circle, and then we go around it. In the beginning, everything is nice, and ACE generalizes to these query images, but then there's this breaking point. The viewpoint change to the mapping portion is too big, and just the optimization fails, the network is too poor, and everything is bad. Until a certain point when the viewpoint change is small enough again and it recovers, and then everything is very precise and crisp and can work again. Right, so how do we deal with this? What can we do? It's not only viewpoint changes. It's also lighting changes, it's objects moving. Whatever change you have which is not represented in your mapping images will cause these problems. The network overfits to the state of the world that it knows and cannot generalize to other states of the world. Right. So it's a conceptual problem, as I said, so we need to change the concept somehow. And the key aspect here is, I think, that this MLP has to do two things. It has to represent a scene. This is something which you want to learn from the mapping images. But it also has to do the actual task of producing the output with respect to the scene representation, the regression task itself. And this is something you don't want to be limited to the mapping images. Here you want to maybe utilize more knowledge about the world. So we need to split it. And this is what we did. The scene agnostic coordinate regressor is now not scene specific anymore. It's a transformer which is fixed and pre-trained. And the thing that is optimized per scene is a scene-specific map code to just a set of tokens. Otherwise, it works like ACE. You have your loss, you backpropagate throughout the mapping stage, and you just not optimize the network, but you propagate through the network and optimize just the tokens. This is the pre-training framework. So now you assume, I have a few thousand scenes to pre-train this scene-agnostic thing. And each scene gets its own mapping tokens. So when you backpropagate data from a specific scene, you update the regressor, but you also update the mapping tokens, but each scene only updates its own tokens, whereas the regressor is a bottleneck which is updated across all mapping images. So with this training setup, you will not solve the problem, because what you get in the limit is just ACE, if it works well. There's no means of generalization in here. So what we need to do is something different, and something which was not possible before. For each scene, we now split the data that we have in mapping data and query data. And in these iterations that I just described here, we just utilize the mapping data, and there's a holdout set of query images which we reserve, which we will not use here. And then in pre-training, we iterate between mapping iterations and query iterations, and in query iterations, we now use these query images. Again, we backpropagate, we update the regressor, but we do not update the map codes. The map codes are frozen. So whatever information is in the query images, it's not allowed to put this into the mapping representation. It's only allowed to update the regressor in a way that whatever is stored in the map codes from the information from the mapping images, the regressor is able to generalize from the query to the mapping representation. And this was not possible before, this split. So when we have pre-trained it, it works exactly as before. So with backpropagation of the reprojection error, we can optimize the map codes, and we see, like with ACE before, we see this point cloud emerging with the geometry of the scene. And it's still 5 minutes. And it's still just a few megabytes large, the map, so that's nice. Although we have this fairly large transformer now, it's still efficient. And what's even nicer is that as we go to the query stage, now it generalizes much better. So it can cope with much more difficult situations now that weren't possible to deal with before. And to exemplify this, again, this toy example here on the left, we have the new approach. On the right, we have the old one with ACE. And you see ACE breaks at some point, but ACE-G, that's the name of the new thing, it's fairly well able to still somehow, even if in these extreme viewpoint changes, give you a good pose. So this was also an ICCV paper, ACE-G, G for generalization. Actually, I find it quite nice, because now you have these map codes are basically a latent representation of the scene. Completely unstructured, well structured in a way that you have multiple tokens of a certain dimensionality, but otherwise it's completely open, right? So it's a scene level feature that you extract via backpropagation of the reprojection error, and that's cool. There are still limitations, so we are not done. ACE-G is not the end of the problem, right? So scene coordinate regression, it struggles with larger scenes, so it's still an open problem, I think. How do you organize map codes in larger areas? What you usually do is a kind of hierarchical approach, so you break down the larger areas into smaller ones, which you can manage with these type of approaches, but the details of that still require research, I would say. What's a clever way of doing that, a very efficient way of doing that? How can you leverage higher knowledge and so on? Lots of stuff to do still. Right. Okay, so what's the next generation of maps? Still, I don't know. I don't know whether it's an unstructured set of tokens. ACE-G is one way in this direction. I like it personally, but I don't know whether this will be the ultimate answer. Still, it's the end of my talk. So thank you, Ed, a lot.